Hello everybody, this is our presentation for the uh, International Materials Research Congress 2024, Cancun, Mexico. Our topic, this presentation, will be the effects of the electric and magnetic fields on the optical properties in semiconducting helicoidal quantum wires. The authors of this presentation are my person Santiago Fernando Machado, Angeli Seth Prada, Ricardo León Restrepo Arango, and we are from Universidad EIA from Envigado, Colombia. For our background, we saw that many laboratories in the world have fabricated quantum wires in nanotubes with helicoidal shape. As we can appreciate in the images, that's how we came to the idea of working on this project. The structure that's developed is a quantum wire made of gallium arsenide, embedded in a cylinder made of gallium arsenide. There's an electric field applied to the structure parallel to the z-axis. The quantum wire is centered thanks to the cylinder that gives a confinement potential, and the method of finite elements is used to solve it. The figure on the right shows the mesh with its partitions. Likewise, a helicoidal quantum wire is made with the same composition, and varying the pitch angle, a form similar to a tree is obtained. It has 4 turns, and as you travel along the z-axis, the radius of the tree changes. This is with the purpose of looking for containment effects provided by the size of the structure. To solve the situation of an electron confined in such a structure, the Schrödinger equation is applied, which has the following terms. The first term has potential energy and magnetic field potential. Second term has potential due to electric field. Third term has confinement potential due to the gallium arsenide and aluminum gallium arsenide elements. Fourth term has potential for impurity found in the materials. However, this last term is not active for this presentation. To calculate the nonlinear absorption coefficients, Boyd-Rober method is used. First-order coefficients depend on the dipole elements and transition energies. A damping term is proportional to the transition of energy level. This model is using 2 levels of energy, the basic level and the allowed transition level. The nonlinear terms described by the third-order coefficients depend on the photon frequency, the transition energy, the dipole matrix elements to the power of 4, and the intensity of incident photons. The presented nonlinear absorption coefficients are the sum of both linear and nonlinear terms. Here is presented the effects of the electric field applied to the probability of finding an electron in a string helicoidal quantum wire. When there is no electric field, the figures left to right describe the fundamental state, first excited state and second excited state. When there is an applied electric field, the figures describe the electron being rejected by the effect of the electric field, consequentially locating itself in opposite direction of the electric field. This phenomena also occurs for the 3 quantum wire. When an electric field sweeping from -30 to 30 kilovolts per centimeter is applied on a string helicoidal, the energy has a proper symmetry and has visible effects on the first 3 excited states, as well as the fundamental state, such that these transitions are allowed and the dipoles are calculated. The biggest dipole is the transition from the fundamental state to the first excited state, followed by the transition to the third excited state, and finally the transition to the first state, where the curve is zero during the absence of the electric field. Finally, on the rightmost figure, there are optic absorption coefficients for each state transition. The energy response of the 3-quantum wire presents a notable asymmetry. Then, the dipoles and the photon energy figures are also present in this section. This last one having a bias towards the red side of the spectrum in its optical properties. For an applied magnetic field on the string helicoidal structure, common oscillations are present on the energy levels and dipoles. The optical properties are in a much more smaller range, situated in a far infrared, and on the left there is the absorption coefficients for the first transition, in the middle the second state, and on the right the transition to the third state. For the 3-quantum wire, the energy level curves are softened, but the dipoles present a less controlled oscillation behavior. The transitions are close between the 3 millielectron volts and 0 millielectron volts, resulting in optical properties placed in a far infrared inside the visible spectrum. Now we reach our conclusions. The energy levels and wave functions of the electron in the nanostructure at this type of finite potential are numerically calculated with the effective mass approximation, using a complex eigenvalue formalism through finite element methods. The calculations of the optical properties are performed within the framework of the compact density matrix approach and an iterative method. The results reveal a significant dependence of the calculated optoelectronic properties on the magnetic and electric field intensities, these responses being in the mid-infrared ranges. And finally, to finish the presentation, we would like to thank the Universidad EIA Colombia through their research project Simulación por el método de elementos finitos de las respuestas ópticas de nanoestructuras semiconductoras aplicadas en imágenes médicas.